check how the QCD effect in the Drell-Yan. Okay, and here also, after you applying the this QCD effect, then you were able to explain why this PT is will be increased with the energy here, because you can imagine this PT will come from if you emitted a gluon, then it will give you some. In order to balance this PT, you got this kick on your original parton, either quark or anti-quark. So they were introducing this PT dependence. However, as you can see, this in describing this PT distribution, it relatively is give a very reasonable distribution as a large PT, but this QCD prediction gets kind of cannot get too much. It's actually get diverge here for the prediction for if you move to the very small PT here, and this is actually can be so at the very large PT, everything can be well described by some perturbative QCD. But if you go to slightly slow PT, then you have to have some special scheme to resumming all of this soft gluon. And so for the TMD stuff we are talking about is on this very small PT region here. And of course, over there is some non-perturbative intrinsic transverse momentum by the parton has to be introduced in this region here. Okay, so I probably spend, let's see, how much time would I get? So I still have half an hour, right? Roughly half an hour. Okay. So maybe any questions? Here is kind of a general introduction about the Drell-Yan process. Any question? Okay. Are you still fine? Okay. Then I would show you is how the, of course I only bring some, I don't intend to be very complete, but I just show you some specific example how the Drell-Yan can be used to understand the Nucleon parton structure. So this is kind of a common cartoon to illustrate. So normally we use the Wegener distribution, which is the most generalized, you say, phase space distribution for the parton inside the nucleon. So you will have the longitudinal momentum information and also transverse momentum information, and also the transverse momentum, transverse position. But over there, because the variable was a lot, so for experimentally, normally we actually most familiar is this PDF. So more or less that was integrated out of this KT and also the R. Then we go to the one dimension, like we only care about the parton density as a function of the X. And then I think you should, for the next generation about this PDF, actually people bring additional, not only the X dependence and also the KT dependence. So there was the TMD stuff we are introduced well by the Professor Mulder in this school. But other than that, we can also, there is another well-studied or intensively developed, which is called general parton distribution, which is actually by utilizing like a Compton, deep virtual Compton scattering stuff, then you will be able to map out of the parton distribution not only on the X but also on the position, on the transverse position, like the impact parameter of these things. And of course, Mark is also the pioneer expert on this GPD stuff. So if you have any question on this, please refer to Pete and Mark. Don't ask me. Okay, then PDF. So I think Kumano-san also showed this. So PDF is not only explored by the Drell-Yan, it's probably most by the DIS using either the lepton beam or neutrino beam, as you will see here by using the lepton DIS or by neutrino DIS, or of course some Drell-Yan stuff here, and also some jet and the WZ production of this. And so there's various quite significant amount of experimental effort. As you can see, the experimentalist has to spend a lot of time taking shift, build up the detector, taking shift, collect all of this the data. And so this is the data set. For example, this is in, I think, collected by Daisy H1. So they use the DIS, which is kind of a space-like process, and the Drell-Yan. Okay. Then by doing the global analysis, if you believe there is some universal PDF, no matter which kind of the reaction process you are looking into it, you will be able to extract out of this Partonic distribution. So this is actually getting from the CT10, which is the CTEC group. I think Tiejun is here, right? Right. If you have any question on the CTEC, you should ask Tiejun. Right now he is in the CT10 collaboration. Okay, so this is a built-in X, which is the momentum fraction carried by the Parton. As you can see, at the large X region, it was dominated by the valence quark, which is U and D. However, as the very small X region here, the dominated part is actually by, okay, I didn't draw the gluon here, but then you starting to see this Sea Quark, like a U bar, D bar, and an S bar. And if you even paid good attention to here, you might see this this three line, this blue, green, and the purple. They characterize U bar, D bar, and S bar. They don't lie on the same. They are simply three different lines. And this Sea Quark, how this Sea Quark comes out? Of course, we are in the. This is kind of the QCD vacuum. So this valence quark inside the proton, they are not something static ball sitting there. They actually interact with each other very strongly through this gluon. So the naive picture how this Sea Quark will come out is actually coming from this gluon splitting. But a naive picture, even though the strange quark mass is slightly bigger than U and D, but in terms of U and D, the mass should be quite close. So you will imagine the probability for gluon go into UU bar should be more or less equal into DD bar. Okay. So experimentally, what you can do is it was a well-known Gottfried field sum rule, is if you experimentally measure the F2 structure function using proton and the minus F2 structure function into neutron, using the neutron, and perform, if you have the experimental data point for this, and you're making this integration can be, in the Parton model, can be split into two parts. The first part is contributed by the valence quark difference between proton and neutron. And the third part is the difference between the Sea Quark, U bar, and the D bar. So naively, if you expect the U bar and the D bar, the X distribution is simply based on this gluon splitting picture, they are identical, so this term should be gone. Then what's already left is only 1/3, and this it's well known, is inside the proton there we have two valence quark and the one D valence quark. So it's based on this Gottfried field sum rule, it gives this prediction about the 1/3. And experimentally we can check this. Okay, so this is how the various DIS experiment in perform, and then experimentally you can measure the difference of this structure function as a function of x. Then you perform this integration. And this show you the integral over integrated here. Of course, there is some kind of a caveat, is experimentally, it doesn't cover up the whole x region. So in order to make in the integration, so you have to making some extrapolation on the unmeasured region here. But even that, you can accumulate that, account that for some kind of an error over there. Okay, so this is the 1/3 based on the very naive picture. And experimentally, experimental measurement of this Gottfried field sum is actually deviated, strongly deviated by this 1/3. And then let's bring the first evidence is maybe this thinking about the symmetric distribution of the U bar and D bar inside the proton is too much naive. Then furthermore, because this Gottfried field sum is an integral over the x, basically we have no detailed idea about the real x distribution of this anti-quark. So however, this kind of x dependent information can be actually obtained by the Drell-Yan. As you hopefully you still remember this kind of a formula, the overall production cross-section is contributed by the probability of the quark and anti-quark. Of course, you can reverse the role in the beam and the target. However, experimentally, actually, we can, by placing the detector in the certain acceptance. So if you put the detector acceptance at a certain region, you can kind of eliminate the contribution from certain term. So you only getting the contribution from, for example, the valence quark from the beam and anti-quark from the target. And over there, you will be able, for example, you use the proton beam, and if you perform the Drell-Yan measurement using the proton beam with deuterium target and also with the proton target, the ratio of it can simply tell you the D bar and the U bar ratio as a function of your x. Okay, then it was the first. So here I want to remind you, so DIS experiment give you some integral information. So they'll bring you the first evidence about this D bar, U bar x might be different than D bar x. However, using the Drell-Yan experiment can give you direct information about this D bar U bar ratio as a function of x. So this was the first Drell-Yan experiment, NA51, that was performed at the CERN, which is show you this D bar and a D bar U bar ratio around 0.2, x equal to 0.2 is actually a factor 2. So they are not identical at all as this region. And furthermore, the A66 experiment performed in the Fermilab get a more detailed mapping out of this structure here. As you can see, it's a very small x. It's a very small x here. D bar and U bar is almost symmetric. But when then it's moved to the large, a little bit large x region here, then it's this their ratio become difference deviate from 1. More or less, the NA51 was kind of a maximum point here. Then there's some trend is maybe it's died down, and around the 0.3 region, 0.3 here, it's maybe some hint is this actually has some kind of a turnover. That means maybe slightly when you go to the large x region, U bar is greater than D bar. But of course, this error bar is quite large over there. It's not very convincing. So of course, there are kind of various physics model how to imagine this U bar could be different than D bar. And actually, the first thinking is actually come from the Feynman. So he just thinking about some poly blocking effect. is the, even though I told you the gluon go to UU bar and the gluon go to DD bar, but originally inside the proton there's already 2U and only 1D over there. So obviously the U quark, maybe the number of the U quark over there is more than D quark. So the phase space, there are more poly-blocking effect for the U quark than the D quark, because already 2U valence quark over there. So that would introduce some kind of a suppressing effect for the gluon go to UU bar than DD bar. So in that sense, it will give you a kind of a natural explanation about why D bar is greater than U bar. But if you perform some more serious perturbed QCD calculation, you find out that that effect is actually quite small relative to what's the experimental measure. And then you have to really rely on some kind of a non-perturbative model, like a meson cloud model. Is the nucleon itself can actually couple to the pi meson. And this anti-quark is actually part of the concan on this pi meson over there. And by utilizing all of this non-perturbative either meson cloud model or chiral quark model, indeed you can describe the observed D bar U bar asymmetry quite well as this 0 to 0.3 region. Okay, so this is a very recent work. Is done by Jen-Chi and I, and also the Tiejun and Zhang Han Lao Shi here. So what we do is actually we are asking is, can we get, because we are interested about whether this A66, they see some kind of a tentative turnover at the large X here, whether this signal can be also seen in the DIS. So we go back to getting the NMC data, as I just showed you. The NMC is the DIS. So normally they check this U bar D bar asymmetry is using the integral form. So instead of using the integral form, actually we get in the difference of the structure function on the F2P and F2N. However, inside here, we have to put into some input is the valence quark distribution. And this valence quark distribution, we get in this information from the most recent parameterization. This is JR14. And this JR14 over there is interesting. JR14 even, we specifically pick up JR14. One of the reasons is the JR14 doesn't require they making the parameterization of D bar U bar go to 0. They don't introduce these negative things over there. And quite interesting, by applying this formula, we actually get finding out there's a consistent evidence for this NMC data, even this DIS, but it's already telling us as the X, there seem to be some turnover of the D bar U bar as the large X region. But of course, it's based on some there could be some still some uncertainty here, and maybe some in terms of the JR14 or some higher order QCD effect.
I'm sorry,
yes.
Look at those data points instead of the solid curve.
So the open point here is the measurement of the A66. So that was the Drell-Yan experiment. And the solid line here is come from NMC, which is DIS. So getting DIS, we only get in the structure function difference. In order to extract the information for the difference between D bar and U bar, we have to fold in some information. This information is the valence quark difference. Of course, you might argue that valence quark, there still could be some uncertainty over there, but we believe the valence quark, because by the DIS, so valence quark information is actually quite well measured. If you go to the very large x here, close to 1, maybe there is some more large uncertainty. But in the region we are concerned here around 0.3 to maybe 0.4, this is actually the uncertainty is quite okay.
So what's the solid curve?
The solid curve is based on NMC data have this difference on the structure function. And I put in the JR14, and this formula in the leading order, you can get in d bar minus u bar. So this is the red curve derived from the NMC data set, and also the
There's
JR14.
no
I'm sorry?
and there's no turnover.
Yeah. There. Well,
Oh, so I'm sorry, I didn't see the curve. Which one?
you have to see the point. Yeah. So the turnover, what I'm turnover right now. Sorry.
So
I
the
didn't
solid
explain.
curve doesn't have a turnover, right? So am I supposed to ignore the solid curve?
No. What we suggest here is actually the solid curve. Here, this region is well known. D bar is greater than U bar. We are bring out the point here. It's actually here is negative. So
So I
that
just ignore the solid curve.
no. We say the solid curve actually bring consistent information as A66 point here. So that was a turnover. So that makes the U bar greater than D bar here. That's the point we make. Sorry,
If
I
I
did.
just look at the solid curve, there's no turnover.
Why? Why you argue that?
It goes to 0 and it stays 0. It's always above 0, right?
No.
But the curve never go to negative.
Oh, you mean curve or point?
Curve.
Oh, sorry.
Solid curve.
I'm sorry.
14.
Yeah, curve is JR14.
Okay.
J is the, I'm sorry. Curve is the JR14 parameterization of D bar U bar.
So I just ignore it.
Yeah. In some sense, I just, okay. I see. Sorry, I misunderstand what you're saying. Right. Yeah, you should pay attention to the point. Yeah. So the point here is from the DIS actually already look like it's give you some tentative information consistent with the A66 observed as the large X.
But just to understand, so the points are corrected for this U valence minus E valence.
Right, and this information is getting from JR14.
But then it's not completely consistent. Yeah.
No. It's consistent. Yeah. Sorry, because the reason we want to draw this JR14 is try to avoid a confusion is maybe inside this PDF, this turnover is already built in. That will affect the extraction here. So we pick up a PDF parameterization, which make just forcefully this go to the 0 without introduce any turnover. So so we only get in the valence quark information distribution from this JR14. And by this formula, coupled with the NMC structure function measurement to derive the D bar minus U bar.
So basically, what we say is for the valence distribution, you believe JR14, but for the C, you don't believe.
Right, exactly. So we actually make several choice of the different PDF. They give a pretty much consistent result. That means the agreement of this UD valence difference is quite consistent within the modern PDF.
Do you also have the valence contribution from NMC alone?
Valence contribution from here.
From
Okay.
NMC, or we can answer.
Yeah, MC will measure the structure function. Yeah. So right. So this is just a very simple algebra of the Gottfried field sum rule. We just reverse it. Yeah. Okay. So previously Gottfried field just integrals. Okay. Okay, I think I got you very rushed. Maybe I will skip some of that. So this is the 906 experiment, which is currently taking data in the Fermi lab, which is Shu-Ying is joined. So there was utilizing smaller beam. So previously 906 is using the 800 GeV proton beam, but right now we changed to the 120 GeV. So this is the kind of data taking. So the data taking, the physics round started in this year, February. So we are going to have some 1 month or 1 month shutdown in the September and resume the data taking. Probably go to the next year. So this is some preliminary dimuon spectra. Of course, you didn't see the high mass, the large cross section as you showed before this, because this dimuon with specific experimental we select some trigger. So there was some trigger effect suppressing the low mass dimuon here. So you see this JIP side, and we would like to focus on measuring this Drell-Yan event here. So hopefully, according to our estimates, then this 906 after 2 years data taking, we will be very clearly map out of the structure according to this error bar accuracy about the how this U bar D bar asymmetry go to the large X. Okay, maybe I will skip this one, but this just tell you in the collider, this you can utilize in the W and the Z to study like charm and the strangeness. Okay, then I will move to the TMD. So even though let's see. So TMD basically, should I spend? Yeah. Okay. So here is the kind of a list of the table. So this is the column, which is the polarization of the nucleon, which is unpolarized, longitudinal polarized, or transverse polarized. And the row here is the quark polarization, which is the polarization of the parton inside it. Or again, unpolarized, longitudinal, or transverse polarized. So in terms of the leading twist of the TMD, you have this choice of it. And specifically, I would like to discuss is actually the Bohr-Motor function, which is as you see, this is named by the Professor Motor. So this is actually the correlation between the transverse momentum of the parton and its own spin. Another thing is the Sievert's function. Sievert's function is actually the correlation is if you transverse polarize a nucleon, how the transverse momentum distribution of the parton were correlated with the overall transverse spin of nucleon. So there was the two correlation function for the TMD. Skip this one. So experimentally, we can measure it mainly in two processes. One is the semi-inclusive DIS or Drell-Yan. So there is various experiments already carried out specifically in the SIDIS. So in the semi-inclusive deep inelastic scattering for the HERMES and for the compass, if you look into the pion production or cation production in terms of the azimuthal dependence, they will be able to extract out of this Sievert's function clearly for the valence quark. For example, this U and a D, they are positive and negative as a function of X or as a function of KT. Because right now you have to remember the different from PDF. PDF only have the dependence on X, but for the TMD, there is another dependence that was on your parton transverse momentum. So this Sievert's function